Good afternoon, everyone. Welcome to our fourth webinar of the Wisconsin Citizen Lake Monitoring Network Winter Webinar Series. This is Paul Skowinski. I'm the statewide educator for the network. Thanks for joining us to learn all about groundwater today and how it interacts with lakes in Wisconsin. Each one of these webinars is recorded for later viewing, so you'll be able to find a recording of today's webinar on the Extension Lakes YouTube channel. On our channel, you'll find a playlist that includes all of our past webinars as well, so it's easy to see them all in a list and watch the ones that interest you the most. I'll send out a link to the recording of today's presentation by tomorrow to everyone that registered, and please feel free to share that link with others as well. I will post a link to the playlist in the chat now so that you can find that easily, so it's in there now. During today's presentation, please keep yourself muted and turn your webcams off. If anyone does unmute or turn on their webcams accidentally, I'll just close those to make sure the webinar runs as smoothly as possible today. Please post all of your questions into the chat box, and I will watch that and read questions to our presenter, Paul, during the presentation. Next month's webinar is all about cool plants. I will be presenting on Wisconsin wetland plants that have unusual features or adaptations. So I hope you can tune in next month on February 24th at 3 p.m. to join us for that presentation too. At this point, I'll turn it over to our guest speaker. Paul McGinley is a water quality specialist with Extension and teaches in the College of Natural Resources at UW-Stevens Point. His research interests include what controls the chemistry of groundwater and how that influences lakes and streams. Thanks, Paul, for being with us today, and go ahead and take it from here.
Well, thank you, Paul. I appreciate the chance to join you this afternoon. Seems like a great day to be talking about 50-degree groundwater, and that's what we're going to try to do in the next hour. It's a big topic, and there's probably a lot we could talk about. And what I've tried to do is distill it down into just a couple of big ideas that I'm hoping to use to try to create a story around Wisconsin, how this large groundwater resource connects with our surface water features, and use that to sort of tell a story about how it influences those lakes and our streams to some extent, and get into maybe a few of the details around there. But I'm hoping this is really just the start of a conversation, and I hope we can continue that with additional questions afterwards or during, and also in the future if there's something you want to follow up on some of the topics I've talked about today. All right, so with that, I'm going to get going here and talk a little bit about groundwater and lakes, and I also want to talk about streams and try to weave some related ideas in on that. And first of all, maybe just a brief overview. I mean, why groundwater? And I'm going to try to make the case in the next 45 minutes that most of the water in Wisconsin is groundwater, and that it really is the source of water to our streams and to our lakes. And it's not just providing water, it's also providing important chemical essential elements, influences the chemical composition of the water, really controls in many cases the chemical composition of the water in our lakes. And it's a pretty fascinating story. And I'm going to draw on information from a variety of sources, weave in some drawings from different researchers. Also want to acknowledge some of my colleagues in our Center for Watershed Science and Education at Stevens Point, in my college, Extension, DNR, USGS, and of course students that have helped in some of this work over the years. All right, I want to make a couple comments at the start. A question that often comes up is, what do we mean by groundwater? So I want to take us through a short experiment here. Envision a jar that you fill with some sand, and then you start to put some water in there. So I'm slowly adding some water to this sand-filled jar, and I think we know what's going to happen, right? That water is going to work its way down to the bottom of the jar, and then it's going to start to work its way up as I am now completely filling the spaces between those grains of sand with water. And so if I continue to add water, of course, that water level in that jar would continue to go up. And I'm going to make the case that this is the groundwater. When I'm talking about this water that's at the base of that jar, filling those spaces around the sand, that that when I'm talking about groundwater in this talk today, that is the water I'm talking about. It's continuous water filling spaces in the geology, and we're going to call that geology. We might call that geology the aquifer. But I'm going to have those spaces completely filled with water. And to make this just a little bit more complete in my jar experiment, I'm going to have to stick a small hole in the side of that jar so that that water can actually leave, because what we're going to make the case today is that this groundwater system, the water in the groundwater system, this water is always moving. And so I'm going to, by having a hole in this jar and I continue to keep adding water in the top, right, I'm creating a system where I have continuous water in the bottom of that jar filling those spaces, and that water is moving. And that's the groundwater system that we're going to try to create today, and then talk about how these lakes are integrated into that system. Okay, so thinking about Wisconsin then, and I will be making some simplifying assumptions today, and my focus is largely going to be on Wisconsin. But let's think a little bit about, we have a lot of water in Wisconsin. We consider ourselves a water-rich state, but where is that water? And if I look at our lakes, and of course we've got thousands of lakes, thinking about that in terms of the area of Wisconsin, that's maybe around 3% of the state. If I look at the streams, we've got thousands of miles of streams. Of course, many of those are not that wide. As a whole, that's probably less than a percentage of the surface area of Wisconsin. We've got lots of wetlands. Maybe that's 10–15% of the state, just looking at the area of those wetlands. But what about the groundwater? I'm going to make the case today that the entire state has groundwater underneath the ground surface, and in some cases very close to the ground surface. And so really that's 100% of the state of Wisconsin. In fact, people have done some calculations on this and said, and you have to make some assumptions, of course, to do this. But they've said if you pull all that groundwater out of the ground in Wisconsin and bring that up to the surface, we would have enough water to basically cover the surface of the state with 100 feet of water. So while we have a lot of water in our water resource features, the vast majority of the water in Wisconsin is really in the groundwater system. That's the system we want to talk about, and we want to try to connect that with the lakes today. All right, well, all of these features, lakes, streams, wetlands, and groundwater are really, of course, part of the water cycle. So thinking about the water cycle, that's this idea, of course, that water is evaporated off the ocean, off the land from vegetation, that evapotranspiration we're going to talk briefly about, comes back, it's condensed in the atmosphere, comes back down as precipitation, and then works its way back through the land and then drains back downhill, down to the ocean again. So we've got this water cycle. In Wisconsin, of course, we're a couple feet above sea level at least, so our portion of the water cycle is really this upper portion here, where I have precipitation coming in and then water working its way through Wisconsin, then ultimately draining back to the ocean. And so I can think about Wisconsin really as a high spot surrounded by low spots, maybe not quite as high as the ones in the upper left here, but look at the ones in the lower right here. We have, thinking about the elevations in Wisconsin, we have a high point around 2,000 feet above sea level. We're surrounded by much lower points, Great Lakes, Lake Superior, Lake Michigan, and the Mississippi River, maybe around 600 feet above sea level. And of course, the ocean would be 600 feet below that. So we're this upper portion of the water cycle, where I have land that drains from areas of high elevation to areas of low elevation. So thinking about Wisconsin, again, we've got those highest elevations are in the northern part of the state. We've got lower elevations on the edges, the Great Lakes and the Mississippi River. And of course, we've got topographic variation across the state, lower areas here in the Wisconsin River Valley or the Chippewa River Valley, and so in the Fox River Valley. But we have this collection of elevations where, in thinking about us in terms of the water cycle, that's water that's coming in as precipitation, falling on the land, and then draining away from the state into these lower areas, the Great Lakes or the Mississippi River. Okay, so let's add that water to that. Typically in Wisconsin, what do we get? 500 hours a year of precipitation. That may come in 100 storms on average. And of course, this varies from year to year, maybe around 32 inches of precipitation. So I'm thinking back to our map here, I'm putting about 32 inches of precipitation on this entire state every year. So this 32 inches is coming in as rain or snow, coming in and basically falling on the land. And then a significant percentage of that is then held as available soil moisture and used by the plants or evaporated directly. So we're gonna combine those two into what we're going to call evapotranspiration. So this is that portion of the precipitation which is used and then immediately sent back up into the water cycle, back up into the atmosphere, of course, where it can condense. Again, in Wisconsin, once again, making some simplifications here, but I would say, we're probably talking around 22 inches on average of evapotranspiration in the state. So getting our 32 inches of precipitation, we evapotranspire around 22. This is pretty good math, right? We can do this. This would be around 10 inches then on average every year that remains. This would be water that comes in as precipitation, but is not lost back to the atmosphere. It's water then that now becomes part of our water resource system. This is the water that's going to flow throughout the state and eventually end up in those lower portions that surround the edge of Wisconsin, right? The Great Lakes or the Mississippi River, and ultimately leave the state. All right, so what we want to do really in the next half hour or so is essentially follow this 10 inches of water and think about how where this water goes is going to influence or interact with our lakes. So let's look at it another way. Instead of looking at the whole state, let's just look at a small portion of Wisconsin. This is obviously a cartoon or schematic, but looking at a map view of a portion of Wisconsin, think about this difference between precipitation and evapotranspiration is about 10 inches a year. And I'm basically adding that to the land surface where it's going to percolate through the ground and then ultimately somehow has to drain out of the state. So here I'm showing this as a series of arrows, but I think we can imagine, right, the only way it's going to get to the Great Lakes or the Mississippi River is it's somehow going to have to work through some of these surface water features, and ultimately most of it will of course end up in some type of a stream and then drain out that way. But the process of getting to that stream is this process of getting into groundwater and moving through groundwater. So I'm going to zoom in here on a portion of this. So I've put a dashed line around at the edge of this schematic where we have a couple of features. You can see I have a lake feature on the right side of that dashed line and have a stream feature on the left side. So I'm going to zoom in on this part and do sort of a profile. So I moved a profile drawing down below, or a side view, another cartoon, and I'm going to try to convince you that what I have this, what would look like a lake up in this upper map is now this lake that's in the lower side view, and this stream that's in the left side of that upper map is now this stream that's on the left side of this. And then I have a land mass or some land between this. And you can picture now, if I'm thinking about this 10 inches a year that I did not move back into the atmosphere, right? That difference between precipitation and evapotranspiration, that 10 inches a year that I am now basically putting into the ground everywhere in Wisconsin. I mean, where is this going to go? And so I'm showing it in this cartoon as working its way through the soil, under these trees here, and then getting into this groundwater area. So again, thinking about that jar that we started with, right? It works its way down there, and then it forms this continuous water zone, which is shown as blue here, but it's really water that's completely filling the spaces between the grains of sand or the rock or whatever this geologic material is that I have there. So it's continuous water. It's completely filling those spaces. Then you can see it's kind of mounded up here between the lake and the stream. So I have this groundwater mass, if you will. That's that water surface, or that groundwater that's between the lake and between the stream. That's at a higher elevation than the lake and the stream. And it's no coincidence that this is at a higher elevation, because this, I can think about this as sticking 10 inches a year into this mass of groundwater, and then somehow that water is going to flow out, eventually get to the stream or get to the lake in this case. but I'm going to try to convince you that actually the geometry of this groundwater, or this groundwater that's mounded up between those two features, that geometry is actually created by that 10 inches a year. By sticking that 10 inches a year in there, the only way for that water to get out is it has to flow, right, either right or left in this simple side view. And the reason it's going to flow is if it's going to flow from higher water to lower water, or we would say higher hydraulic head to lower hydraulic head. We can get into some of those details in a few minutes, but it has to have higher water in the middle to flow down to the lower water on the edges. And so then it adopts this geography, or this topography of the groundwater, or this mound of groundwater, based on how high the water has to get in the middle to actually move that 10 inches of water to the stream, or that 10 inches of water to the lake on the other side. So it's not just adding 10 inches of water to a groundwater system, it's that 10 inches of water that's creating this groundwater system, creating this geometry of what we're going to call the water table, or the geometry of this groundwater system between the lake and the stream. As Paul said at the start, I'd encourage you to put some comments in, or questions as we go along. If there's anything we want to spend a few more minutes on, or if you've got a question about something as we go through this, it would be great to try to address those as we talk about.
Paul, I had a couple questions emailed to me earlier. I think they relate to what you have on the slide right now. The first question was asking about using groundwater measurements as a measuring tool instead of a lake level gauge or a set ordinary high water mark. And basically, would you be able to use the groundwater level as a way of measuring the lake level or not?
That is a great question. So, I mean, let me make a quick try at it here. And I think as we go along, maybe we will kind of try to weave back to that a little bit here. But I mean, the case I'm trying to make here, and will continue to try to make, is that these lakes and streams are really exposures of this groundwater system, right? Most of the water is in groundwater, and in the streams really are those low areas that act as drains. And the lakes are really low spots in the topography where the water table is essentially higher than the groundwater, higher than the ground surface. And so thinking about this profile drawing here, you can see where that groundwater level then gets to the lake, and it just continues. So this is an exposure, if you will, of the water table, just like the stream level is sort of an exposure of the water table. So, getting to that point, there will certainly be a connection then between the groundwater level that's very near a stream or very near a lake, in most cases, and the water level in that lake, because these are, to some extent, we're really looking at the same thing. The further you get away, of course, you're going to, going back to this concept of actually building up a higher groundwater level between the stream and the lake in this case, which is created by the fact that I'm adding new water every year. This water, this elevation, the groundwater, say in between the stream and the lake, and this center part is called the watershed divide, because in this place, at that location, the groundwater on the one side is flowing to the stream, and the groundwater on the other is flowing to the lake. That could be quite a bit different elevation than we would have downstream. And in fact, these elevations at the groundwater divide of the groundwater would tend to be much more variable than the elevations of the water in the stream or the lake, because as that amount of, if that 10 inches is not 10 inches for 2 or 3 years in a row, maybe you're getting less water going in because you get less precipitation for a couple of years, then you could picture you're sticking less than 10 inches in, that water level, that groundwater level at the divide is actually going to go down. Or you could have a couple successive years where you put much more than 10 inches in there, right? We're going through a period of a couple of wet years. Now we're sticking probably more than 10 inches on average in there. And then that groundwater level is going to go up at the divide. We'll continue to come back to that. But Paul, if we want to, if I don't quite address that as we go on, let's come back to that question. A little bit of terminology here. So we have that surface of the groundwater is sometimes called the water table, right? So going back to that description of the groundwater earlier, right, where it's that area where the water is completely filling the spaces between the grains of sand. The top of that saturated surface is often referred to as the water table. And, in this case, then, of course, and it goes to that previous question, that water table is the elevation then of the groundwater. And in this case, of course, we're showing how that varies from the divide all the way down to the stream and all the way down to the lake. Another way of thinking about this groundwater system is that it's water that is moving, right? It's right here, it looks like a groundwater, a mound of groundwater, but it's really groundwater that has new water coming in and old water leaving. And so we can think about that in terms of a flow path for the water as it's moving through that system. So some of that 10 inches a year that enters close to the groundwater divide is going to get to the water table. Now it's eventually going to drain to this stream feature, so it's going to be flowing down and eventually discharging to the stream. Whereas if it fell over here and worked its way down, it would be going to the stream here. So I'm showing that as a couple of stream lines or flow lines, showing that the groundwater is not moving rapidly and it's traveling relatively slowly. We could be talking feet a day or inches a day, and so it's moving slowly and kind of following these lines as it's draining to these surface water features. As a result, of course, it could spend quite a bit of time on the ground. It could spend decades to go from the divide to the stream, or maybe several years if it entered much closer to the stream. I think another useful way to think about this groundwater system is to think about it in terms of a water budget, because the other, we're saying that every year we're putting about 10 inches of water into this groundwater system, and that water is also then the water that's draining out to our lakes and streams. It's obviously not the same water every year, because it could take a decade for some of that water or more for some of that water to enter the groundwater and then travel to the stream, or it could take less than that. But if on average that water table elevation doesn't vary a lot, then that means that the water that I'm putting in must be more or less equal to the water that's going out. And so another way to kind of evaluate this 10 inches a year that I'm talking about would be to look at the amount of water that's actually flowing in the stream. And we could do some math on this, and I want to do a quick example on that, and you can check these calculations later. But let's assume for discussion purposes that I'm just looking at 1 square mile of land in Wisconsin. So that'd be 5,280 feet on a side, a square mile. And I'm thinking about the amount of water that's entering that square mile every year. And we say, well, it's about 10 inches, the difference between the precipitation and evapotranspiration. Well, it turns out that's around 23 million cubic feet, which is pretty amazing in itself, right? This is 1 square mile of Wisconsin. We're talking about gaining 10 inches of water on average. And I should point out, I mean, this is going to vary from different parts of the state. And I'm kind of doing sort of an average here at 10 inches, and we can talk about some of those details later, but for our sort of our storytelling purpose, about 10 inches a year would mean 23 million cubic feet of water every year is entering in every square mile. Well, that's a big number, but if that water is actually slowly draining out of that square mile, right, thinking about that profile diagram, then maybe I would think about that 23 million cubic feet of water emerging from that square mile rather uniformly over the 31 million seconds I have every year. Well, if that's the case, that means that every square mile is generating around 3/4 of a cubic foot of water every second. So let's think about, what does that mean? 3/4 of a cubic foot. I mean, a lot of us aren't used to thinking about cubic feet, but that is about 5 gallons. So what this means is that every square mile in Wisconsin, on average, and once again, we're simplifying, there's going to be some variations here, but every square mile in Wisconsin is generating about a 5-gallon bucket of water every second, just from that 10 inches of water every year that I get from that difference between precipitation and evapotranspiration. So when you were thinking, one way to think about this would be if you're thinking about a spring or some water that's emanating from the side of from a hillside, and this is probably groundwater that would be coming out, and let's say I'm filling a 5-gallon bucket every second, which would be a fair amount of water. That's that's about the amount of water I would expect if I was just taking the 10 inches across that square mile above that and uniformly distributing it over the course of this year, next year, and the year after, and the year after. So that's sort of the water production side of thinking about this groundwater resource system in Wisconsin. And we can actually test that at a much larger scale. So here, showing the Wisconsin River. Wisconsin River originates just on the edge of the Upper Peninsula of Michigan, flows through the state, comes out at the south here, southwest in the Mississippi River. There's a gauging station pretty close to the edge here in Muscadet. And that Wisconsin River, it gets water from a watershed or a contributing area that's around 10,400 square miles of land. Right? So that's this, I've roughly outlined it here, but they would use the term Upper Wisconsin, Central, and Lower Wisconsin. This is that land area where that we could think about it as that 10 inches of water every year is ultimately ending up in the Wisconsin River. And if you go to Muscadet, where they have the USGS gauging station, that's a pretty big river there. So here we're looking at, this would have been October year before last, Wisconsin River at Muscadet, pretty wide stream, of course, at that point. Well, I think we can do the math, right? At 10,400 square miles of land, and knowing I get almost 3/4 of a cubic foot of water per second per square mile, it's probably not surprising that the average flow at Muscadet is close to 9,000 cubic feet of water every second, right? So it's kind of a lot here in terms of the math, right? But basically what we're saying is that flow in the Wisconsin River is not unrealistic, or is about what we would expect if we think about that Wisconsin land area generating around 10 inches of water per year, and more or less that kind of uniformly showing, or more or less showing up over the course of the year in the Wisconsin River. All right, let's get back to our groundwater a little bit here. So now that we've kind of made the case here that I hope that we've created this water table surface that reflects this addition of water that we get every year in Wisconsin, and we end up with a water table configuration that reflects the drainage pattern of streams and also the amount of water that's coming in every year. Maybe we can think about mapping that water table surface. So if from year to year this variation is not a lot, then that water table surface is much like a topographic surface, and I could map that just like I would map the topography of the land. It's not going to be quite as static as the land, because we know that the water table surface can vary, that elevation can vary if I get more or less water in it from year to year. But I can create a map just like I would create a map of topography. And so here's an example, and I have the kind of the start of a water table map above, where I'm showing sort of a circle of water table elevation of around 1,400 feet above sea level, which kind of mimics sort of the top of this groundwater divide that I'm showing in this lower portion here. And then if I extend that out, you can see I'm showing here groundwater contours, lines of equal water table elevation, higher in the middle, lower as they go away, going to a lake feature over here, going to some stream features down here, just a little bit north of Hayward. This is the Cable area in Bayfield County. A great study. This water table map is available. Oops, I should have gone back to that. This is a study that was done by the State Geologic and Natural History Survey, and that is available as a report. And they have a nice discussion of their water table map development there. But you can see what we're looking at here is a mapping or an elevation surface of the water table, and some arrows were drawn on here just to demonstrate, okay, this is higher water here, and then that water is flowing away from those areas of higher groundwater, and of course ultimately draining to lakes and streams. And then we look at the surface water features in there, and going back to our earlier discussion, those are elevation. Those can also be shown as elevations here, and we can see that those elevations are consistent with these features essentially being connected with that water table surface. So where we get to a stream feature where we're in a low spot in the landscape, that's where the groundwater is draining, and so we have the groundwater level and the stream elevation then would be coincident, and similarly in the lakes. So as a result, this groundwater system, which I continue to keep adding water to, every year or throughout the year, and then the water is flowing, draining to streams, becomes sort of this base flow or this continuous source of water into our lakes and rivers. And so what I want to do is get into maybe just a couple of examples of how we see this influences our lakes and a little bit on our streams. So let's get into the water and think a little bit about temperature and chemical composition. Before I do that, Paul, are we doing okay? Do you think we did okay on that question? That anyone want to pick up on that?
Yeah, I think you answered it, Paul. The person who asked is on the call, so if they have any additional details or want to ask anything more specific, then they can certainly do that.
All right. Definitely a strong, case we're trying to make here, and we can always find some exceptions, I'm sure, but this strong connection between the continuous water table surface and most of our surface water features. And it's just that the further we get away from those features, the greater the difference in elevation between the groundwater and the water surface, the water elevation in those features will be. All right, so here we're looking at a stream that's actually strongly connected with groundwater. And in this experiment, this next experiment or this next example, I want to talk about a little bit of temperature monitoring that we did in here. So this is a stream that's draining in central Wisconsin. It's a pretty strong groundwater connected stream. So on a cold day like this, we would still see some water flowing in the stream. But we were out there in September 2019 and doing some temperature logging. So we put some temperature sensors in the stream and in the air. So I've got a water temperature sensor, or put a temperature sensor in the stream, put one in the air, and then pushed one 6 inches below the stream bottom. So kind of a sand bottom here, and kind of inserted that temperature probe 6 inches into the bottom of the stream. You can see that the air temperature here varying quite a bit, warmer during the day, of course, colder at night, some variation. Water temperature kind of mimic that a little bit. As it would warm during the day, it would warm in the stream, warm during the day, it would warm in the stream, and then on a colder day, it would be colder in the stream. But you can see that the temperature sensor in the bottom of the stream, the temperature never varied at all. This was a spot where the groundwater is actually draining directly into the bottom of the stream. It's moving right from that higher elevation in the landscape to this lower elevation in the stream. And so I'm pushing, essentially it's pushing groundwater into the stream. Groundwater has a relatively consistent temperature. And so around 49 degrees here, a little bit less than 49 degrees, but close to 9.5 degrees, 49 degrees Fahrenheit, 9.5 degrees centigrade. And so that's very similar to what we were talking about, right? I've got higher land adjacent to this stream, gaining water every year from that difference between precipitation and evapotranspiration. That water is flowing downhill, of course, leaving Wisconsin, but it's draining to the streams. In fact, it goes up a little bit in the stream, right? So we talk about flowing from higher elevation to lower elevation, but it's also it's flowing up into the stream because it is driven by that hydraulic pressure generated by that higher water table elevation here, and draining to the stream. So if I stick that temperature sensor in the bottom of the stream, I'm going to be measuring in this case, I'm going to be measuring that groundwater temperature as it comes into the stream. And an example that we might see frequently in the winter would be this one, right? When we're looking at, another example of where 50 degree or 48, 49 degree water discharges into lakes would be the portions of the lakes where I'm going to see later ice formation or early ice melting, because I'm sticking water into that lake that's much warmer than the 32 degrees where it would freeze. And so I'm going to prevent, until at least this air gets very cold and can take all that heat out of that water, I'm not going to see any ice here until it gets that cold. So these might be the areas where these would be the areas where that lake would be less likely to freeze or more quickly thaw in the spring. Because when I think about groundwater temperatures at 50 degrees or 48 degrees Fahrenheit, that's certainly pretty warm water in the winter. Finally, maybe a couple of comments at the end here about thinking about adding one additional condition to this, and that is not just thinking about the amount of water, but what about the influence on the chemistry of our lakes? And so this kind of gets to this question of, all right, we've been spending a lot of time talking about 10 inches of precipitation being turned into groundwater and then moving through this water resource system and draining to our lakes and streams. Well, what about the chemistry changes as I'm moving that precipitation through the soil profile into the water table, or into the groundwater, and then how it's going to travel in the groundwater? I'm going to be probably changing the chemistry of that rainfall in this process of making groundwater. And then ultimately, of course, since this is the water that ends up in our lakes and streams, the chemical characteristics of that water are also going to influence those surface water features. So I've got a lot on this slide, but let me just try to summarize sort of a story on this. And that is, when we think about rainwater, it really is pretty soft water, pretty acidic water. We think about back to our water cycle, that that was water that was formed by condensing water vapor. So it's basically taking almost everything out of the water, taking the water vapor and then making new water. So I have water that has, or making liquid water. So I have water that has relatively low calcium concentration, for instance. I'm showing that here is 0.3. It's going to have a relatively low pH, could be 5, 5.5, upper 4s, depending on where I am. So I'm going to have a low pH acidic water with very little mineral content in it. And I'm going to put that water, of course, on the land. Then it's going to work its way through the land to get to the water table. And in the process of doing that, it's going to be subject to all that biological activity that occurs in the soil profile. So I have all this biological activity, decomposition of organic material, microorganisms that are releasing carbon dioxide. When they release that, the percolating water takes that carbon dioxide, that actually becomes an acid, a carbonic acid, which will then dissolve some of the soil and mineral material that are in that soil profile. So by the time that water gets to the water table, and the reactions can continue to occur as it's in the groundwater, but I have now taken this low pH, low mineralized water, and I have really increased the pH, and I've increased the mineral content. And in some parts of Wisconsin, we would use the term hard and mineralized, because we do have geology that has a lot of minerals, different types of minerals, carbonate minerals. They can actually dissolve a lot of calcium and magnesium into the water as it's moving through the soil and rock. So I end up with a much different chemical composition of the water. So if I only relied on rainfall, of course, you heard a little bit about this in last month's webinar. If I have a situation where I don't have a lot of interaction with the groundwater and I rely on precipitation that has a low mineral content, I'm going to end up with a much different biological system than I will if I'm putting water in there that has groundwater dominated water source, because I have all of these minerals that are already in the water in a much higher pH. So that varies across Wisconsin. So thinking about lakes in Wisconsin, their interaction with the groundwater, and then the chemical composition of the groundwater. I'm not going to spend a lot of time on geology here, but we do a lot of water testing in our laboratory at Stevens Point, a lot of private well testing through some of our educational programs. We have a mapping application on our website. I just pulled this image off of that a couple of days ago, where we map the results of that testing and some of the things that we look for in those waters. And we average the results of the testing over an area, different areas of Wisconsin. You can look at this by the county or by a township. And so here I'm showing hardness. Hardness is the amount of calcium and magnesium in the water, which is really a reflection of the geology that the water is moving through as we're converting this precipitation into groundwater. So I'm showing on this side carbonate rock from Door County. And if I look in that area and along here, I have some of the red and orange colors on this map, which is water that is really hard water. So I have a lot of calcium and a lot of magnesium in that groundwater, because as it's worked its way through the soil profile, it's dissolved some of that rock, those rock materials. As opposed to maybe Jackson County or up here in northern Wisconsin, I have areas where I have very soft water. So less than 50 is what I'm showing in that dark blue. So if some areas here we have very little carbonate mineral in that geology, the sands and gravels from the glacier or some of the bedrock. And so when that groundwater when it moves through those soils and through that groundwater, I don't acquire the hardness that I would in other parts of the state. Well, you can imagine this does influence lakes. And so I want to wrap up with a couple of slides looking at a lake in central Wisconsin, right here where it's kind of yellow, so the eastern part of Portage County. So I've got relatively hard water. I've got hardness of around 200 to 300. These are just hardness units, so we won't get into details on that now, but we can talk later. And so I'm zooming into this portion here, and I'm going to show that as some streams. We don't have to or everything labeled here, but on the left, this is the Wisconsin River working its way through the eastern part of Portage County. On the right, we have the Tomorrow River, becomes the Wapaka. Eventually, this ends up in Lake Winnebago and then out to Green Bay. So we're really looking at an area here between the Mississippi River drainage and the Great Lakes drainage. And now we're showing these as streams and some lakes in there, but from our earlier discussion today, if I zoom into a part of this, we know that there's actually a continuous water table surface connecting these streams and lakes. And so what I'm showing here in these dark blue lines these are simulated, but they line up pretty well with the measured maps. I'm just trying to use something that's consistent here. And I have the water table contours. So this means that there's a water table elevation of around 1,100 feet in the middle, and that gets down to maybe around 1,000 feet. So a water table drop here, or water table topography that goes about 100 feet down from the center part of this map to the eastern part. This may be 6-7 miles here, something like that. So I'm looking at a continuous groundwater surface connected to these streams and connected to these lakes. So this water resource feature, what we might think of the streams and lakes, is really connected to this water table. And I'm interested in specifically looking at a lake down here in this lower portion of the drawing. So I've got a couple of lakes down here, and you can see, thinking about again, our drawing, right? This is the high part of the groundwater on the left, and then it's dropping as I go to the right. And when I zoom in on that, now I'm looking at, once again, right, a high groundwater on the left, and that mimics, going back to our earlier profile drawing, right? That would be an example of a groundwater divide where it's flowing to the east, flowing to the west in the one direction, and then in my area it's flowing to the east, right? So I'm at that divide. I have a lake over here that I'm going to look at, Fountain Lake, and that's very similar to the lake that we showed in our profile drawing. So thinking about that water moving, in this case, from the divide, and then continuing to gain water course. It's coming in the ground and then flowing this way, continuing to flow to the east. Fountain Lake is a pretty small lake. And it's headwaters of Emmons Creek, so it has a stream that drains out of that lake. So small lake on the edge of this thing. And so thinking about this water table system here, and if I were to use some computational tools where I could try to figure out, based on where this groundwater is flowing, what's that land area that's going to drain that groundwater in the direction of this lake. And it's about this area. So it's maybe a couple of square miles of land going from the divide to Fountain Lake. And the thing, as we've been thinking about this, right? So thinking about this profile view, that is the area where that roughly 10 inches a year or so is coming in, working its way through the ground. After a portion of it's evapotranspired, that 10 inches entering the water table, it's flowing downhill, if you will, and draining to this lake, and then eventually possibly coming out in this lake. And so then that becomes that water volume then that's contributing water to this lake. Well, we can experiment a little bit here, and we have. So one tool that we have to kind of figure out where that groundwater is coming in the lake is something like temperature, right? Many of you have observed this when you walk around a lake and you can kind of feel those cooler areas coming in during the summer. We can measure that with a temperature sensor. Also, another way is to use a little pipe or a little tube. And so here's one of our students, Chris, is working on the edge of a lake, and he's sticking these small tubes in there, just a temporary well, if you will. They have a little bit of an opening on the bottom, pushing those in on the edge of the lake bed, and then looking at the water level in those tubes. And if you're in an area of the lake where that water is really draining into the lake, well, it's draining from areas of higher hydraulic head or higher pressure to lower pressure. So there will be a higher pressure, if you will, higher water pressure in the bottom of that tube, if that's an area where the water is actually coming into the lake. and that will increase or raise the water level in that tube above the lake water level if that tube is open, deeper below the base of the lake. And so we went around this lake, and then these areas that were shown as triangles here are areas where it was pretty clear there was higher water pressure or higher pressure below that lake bed. And so these would be areas of groundwater inflow, where the groundwater is draining this lake. Of course, kind of what we would expect, right? We know this as a land area that's draining to it. We can even measure, in this particular case, this has a stream coming out, and there was around 1.5 cubic feet of water per second coming out of Fountain Lake all the time, right? And this would be consistent with our 10 inches earlier, right? If we have a couple of square miles or a little bit more draining to this lake, I know that I probably have around 3/4 of a cubic foot per second for each of those square miles. So 2-3 square miles is going to get me, a couple of cubic feet per second of water coming out, consistent with what we measured in terms of the pressure in the tubes around the lake. Finally, my last couple of slides here as we're wrapping up. So let's think about, now we have this hydraulic connection with the groundwater in the lake. We have a fair amount of water moving into this lake. What about the chemistry of that? This is an area where we said was relatively hard water. So we were in that kind of 200, 300 total hardness. And something kind of interesting goes on in lakes like this, where we have really hard water coming in, a lot of calcium in that water. Of course, we said that calcium was in that water because that rainfall, as it's moving through the soil profile, is acquiring that carbon dioxide and then dissolving those minerals. Well, now you're carrying a water that has a high mineral content and also a high carbon dioxide content, and you're carrying that into the lake. And then once it gets into that lake, things start to change. That water is now released into the lake, where some of that carbon dioxide will be released to the atmosphere. The pH can go up, and through a couple of chemical reactions, we end up with a situation where when there's real high hard water, when this high hardness water ends up showing up in the lake, I can have that calcium from the hardness combined with some carbonate, and we don't need to go into a lot of detail on that, but the conditions change when it goes from groundwater to lake, and I can actually form a calcium carbonate or a solid material that then we can see encrusted on plants, or in some cases will accumulate on the bottom of the lake. Sometimes this is referred to as marl. But I think it's also just a great example of how we get that strong groundwater to lake connection, and how that chemistry of the groundwater then can influence the chemistry of the lake. And we can measure that. So looking at calcium concentrations, for instance, in Fountain Lake, we see that during the course of the year when the water comes in the winter, and then relatively high hardness, and then with all that biological activity in the spring, and then we end up with a drop in the hardness in the water, and then it goes back up again. This is a water that has a lot of water flow, so we see a relatively dramatic increase and decrease in the calcium concentration during the course of the year. Well, Paul, I think I've used up all my time, but in closing, let me just make a couple of quick comments. I'm hoping I'm making the case here, and I look forward to talking more about this. The groundwater is a vast, most of the water in Wisconsin is groundwater, and that this large groundwater resource system has water that is always moving, and our lakes and streams are really part of that system. And so when we're trying to understand the source of our water in our lakes, and we're thinking about the chemistry of our water in our lakes, and a lot of this has to do with this close connection between the groundwater resource and our surface water resources. Hopefully we can certainly continue the conversation, and by all means reach out to me afterwards if you have questions or comments or things you think we should talk differently about, or things that we could change when we start talking about this connection between lakes and groundwater. Thanks for your attention.
Thank you so much, Paul. We have several questions in the chat. If anyone has additional questions, please just put them in the chat now. We'll wait a minute for more questions to come in. While we wait, I'll put the registration link to next month's webinar in the chat, so you have time to click on that and register for next month if you'd like. And I'll start reading the questions that we already have so far in the chat. Paul, first of all, how do you actually measure water flow when it's underground?
Well, that's a great question. as you know, I mean, I didn't specifically talk about measuring water flow underground. You know, one of the reasons, I guess, why I would think about the stream connection, you know, I think a good way to think about this, this groundwater quantity is really that water budget between, if it's coming in as, and I didn't use the term groundwater recharge, but when I think about that, this difference between precipitation and evapotranspiration is this amount that we're recharging the groundwater with every year. And that ultimately is the water that's going to come out of the watershed. So maybe the easiest way for me to think about the amount of water moving through that system is to try to measure the water that's actually leaving the system, not actually how it's moving within that system. But, you know, it's a great question. I mean, we also try to estimate water flow because in the ground, that water is moving through, say it's moving through a sand material. I mean, we know that we can make some reasonable assumptions that the rate of that water movement is a function of what the difference in elevation is from one end, from one side of that water table to the other. You know, what's the drop in the water table, and then some characteristic of the media. So I guess going to that question, and now that I'm thinking about it, right, they're probably thinking about when I said, oh, maybe it moves about a foot a day. That would be an estimate that we would probably make based on what the slope of that water table surface is and what are the characteristics of that medium or the aquifer through which the water has to move.
Okay, moving on to the next one, we have a couple of questions about lakes, seepage lakes with no inlets or outlets. First of all, in a seepage lake with no inlet or outlet, is the cause of lake level change primarily due to the amount of groundwater and therefore precipitation?
That's a good question. I guess I would, and there's probably a lot of complexity we could add to that, but I'll try to make maybe set up two extremes on that. I mean, on the one hand, if that, you know, and thinking back a little bit to the blog presentation last time, you know, if that lake is not that strongly connected to groundwater in the sense that most of the water in that lake is coming from precipitation, I mean, I could see where maybe we would have, you know, you could be more strongly influenced by the immediate changes in the amount of rainfall. In general, though, I would say I would look at these seepage lakes as really exposures of the water table, and so the water level change in the seepage lake probably mimics the water level changes in the aquifer itself, in the groundwater itself. And as a result, though, those lakes that are closer, say, to what we were showing as a groundwater divide, the lakes that are closer to that divide are probably going to be subject to much more variation in water level, because the groundwater level variation is going to be greater in the areas closer to the divide than it is going to be near those stream features. And you get near the stream, we do have all of that water from the divide moving towards that stream, and those water levels don't change. You know, think about the water levels in a stream. They don't change nearly as much as the water levels would change close to the groundwater divide.
Okay, there was another question about seepage lakes with no inlets or outlets, how the chemistry works in those systems, or is it different between lakes that have inlets and outlets and those that do not? Yeah,
great question. You know, I would look at most of these seepage lakes as having some connection with the groundwater, the extent that, you know, and so we're still probably, and we certainly measure this in some of the seepage lakes that we've looked at. If we go around these lakes with these little tubes or mini piezometers, we can certainly find in a seepage lake that doesn't have any inlet, or doesn't have a surface water inlet or outlet, it's still going to have a groundwater inflow and probably a groundwater outflow. And so I didn't show any of those examples here. The one I used was Fountain Lake, and it does have a surface water outflow. But if that was just a seepage lake sitting in the groundwater system, there's still, you know, physically the mechanism is there for the groundwater to move up into that lake, move across the lake, and then move out the lake on the other side. And so when we stick our little mini piezometers or little tubes around that lake, we're going to show, typically, we're going to have inflow on a portion of that and outflow on the other portion. Probably the important question that goes, and that's a little bit harder to determine, and goes to your question is how much groundwater is coming in. And certainly that's going to influence the chemistry, because that's going to influence that balance between groundwater and precipitation as controlling the chemistry. And then I think we would have to look on a lake to lake basis as to what does that water table look like? Are we really close to the groundwater divide? Are we further down in the groundwater flow field? And then maybe actually we could use some other tools to try to evaluate what the chemistry is telling us about that balance between the groundwater and precipitation as controlling the water budget for that lake. That's a great question too.
Great. We had another question, or somewhat of a comment about heavy rains causing basement flooding. Roger mentioned that in his case, the lake level and basement floor levels are about the same during a normal period, but then during a heavy rainstorm, they see a lot of quick filling of sump pumps. And heavy rains sometimes raise the lake level more than 2 feet in a matter of hours.
Yeah, so right. So I guess the question is getting to it's not that our response to the storm isn't just the entire water table, but that we also have local flow, whether that's directed flow or somehow getting into the geology around this lake, so that I have the water table or the subsurface water just near the lake is actually responding more quickly maybe than the entire water table surface. Is that the question on that, Paul?
Yeah, I'm wondering if maybe there's some sort of a more direct conduit to the basements, rather than the water showing up as an immediate effect in the basements from just groundwater seepage, or maybe there's some other more direct way that water is quickly getting to the basements.
Yeah, I would agree. And that might, we could maybe explore that in a little bit more detail. Maybe that goes a little bit to my comment at the start about the simplification, right? We think of, when I'm talking about groundwater in this presentation, we're thinking about groundwater coming in, it's all kind of flowing. Imagine the geologic complexity if we have areas with sand and you've got layers of silty material, you've got some peat or some organic deposits, right? So we could have flow pathways, and like you said, Paul, directed surface flow that's then adopting different patterns rather than just kind of moving like that water in the jar that I presented in the first slide.
Yeah, another question here is asking about seepage lakes and springs. Do all seepage lakes have springs? Maybe touch on the difference between a spring and just groundwater seepage.
That's a good question, because I probably wouldn't make much of a distinction, or wouldn't make a distinction between springs and seepage, in that I'm looking at this as this is subsurface flow that's entering our lakes, and it's the result of water that was generated on the land from that difference between precipitation and evapotranspiration, and that area where we're witnessing it, the edge of the lake or whatever it is just downstream, if you will, or down gradient of where it entered. And so it could maybe seem a little bit more localized, and maybe this goes to maybe a little bit more complex or heterogeneous media in a lake, where maybe, because it doesn't all come out uniformly in the lake, and it has a tendency to come out maybe closer to the shore, but that can vary a little bit depending on the geology of the lake. So maybe it tends to get a little bit more focused in some of the geologic materials, and so then you have more in some areas than the other. But I would still view it all of this just as groundwater.
Okay. Diane mentions different chemical testing that's done with lake water, and she wonders how we would know what kind of chemicals are specific to the lake and what is coming from the groundwater.
Oh, that's a good question too. Well, I guess the answer, I probably don't really know exactly, but if I was going to try to guess, I would say we could, if we knew something about the chemical characteristics of the groundwater, which maybe I could get from, we could do some evaluating of the water in wells in that area. And once again, that can be tricky because that can be variable too. And then we would try to make a comparison between that and what's in the lake and see if, in many cases, the lake will modify that. Thinking about our simple calcium example here, where, I'm going to have less calcium in the lake than I'm going to have in the groundwater because I'm going to actually precipitate some of that once it gets in the lake. Similarly, of course, I could have chemicals that enter the lake through surface runoff adjacent to the lake, which are going to be different than the chemistry of the water that's actually coming in the groundwater. So a good question, but not sure I have a good answer for it.
We have one more question for you. How does one determine the divide for a specific lake?
Well, a great place to start would be a water table map. And our state Wisconsin Geologic and Natural History Survey actually has done a fair amount of water table mapping in Wisconsin. So a lot of the counties, there are water table maps available, and you can go on their website and you can look at the maps that they have there. The other, in the absence of that, I guess we could look at a stream network and we could try to make some observations about where the divide is likely to be. I mean, because, ultimately the water has to leave in some way. So we know it's draining to these streams. And so we could kind of look at those streams and kind of maybe map something up, but that would certainly would not be a great substitute. It would just be a first cut compared to what you would get, say, if you were able to look at a water table map.
Perfect. And we are at 4:01. So thanks again, Paul, for presenting today. Thanks to all of you that have joined us for today's webinar. Remember that next month's webinar on unique lake and wetland plants is on February 24th at 3 p.m. And with that, I hope everyone has a great evening, and we hope to see you back here on February 24th.
Thank you.